Well, this is a talk that I would like to make an evaluation and some thoughts about how we can reconstruct the occurrence of pre-existing structures in a fault and thrust belt. So I will use the example from the Betics, some examples from the Betics and also from the Hellenides and the Albanides to talk about this. So this is a summary of different publications with the participants of many colleagues from Albania, from Austin, from Greece, and from Spain. And so let's start. Okay, so this is part of a collaborative effort with the participation of many institutions. I would like also to acknowledge the invitation to give this short seminar. So it is very well known in fault and thrust belt that the occurrence of evaporites are very important as detachment levels. So for example, Arbel Valley highlights that, or Ana Somaruga and other people. This is very well known. But my point here with this presentation is to discuss how we can reconstruct or evaluate the occurrence of previous salt diapirs, because it is very well known. I'm going to use the pointer. It is very well known that when we have previous salt diapirs, they are controlling the final geometries in a fault and thrust belt. So the occurrence of salt diapirs in basins, it is very well established since the 40s or even the 30s. This is an example from a salt diapir experiment in the 50s for the Gulf of Mexico. And this topic has been studied by many other people. So I am not going to really make a major advance on this, but any one of you who are interested in this contribution of previous diapirs, you can use or check the important contributions by Mark Rowan, Bruno Bendeville, Jean-Paul Callot, or Letoussey. So my point is that I would like to evaluate how we can reconstruct the occurrence of previous diapirs and how they are controlling the final geometry in the fault and thrust belt. I will use two examples. One is from the Betics. So in the Betics, it is a very tight orogenic origin between the Betics and the reef. It is in the Western Mediterranean. And one of the most important and intriguing aspects in the Western Betics is that we have very large outcrops of Upper Triassic evaporites. So in this region, we have the classical three phases of the Triassic. We have the Keuper phases, that is Upper Triassic, is evaporitic. We have the Muschelkalk, this middle Triassic is carbonate rich, and we have also the Buntsandstein, is lower Triassic and is more detritic. And for us, it will be important to reconstruct and to see how the Triassic, Upper Triassic evaporites are important for this origin, in particular for the external Betics. So we have all these illustrations are from different papers with Johan Flink, and we have made a major revision in the area, not only using surface geology, also integrating well data and seismic interpretation. I think that this is an important benefit in any orogenic belt, is to incorporate surface geology with subsurface data. So for example, here in the Western Betic, you can see the massive occurrence of a very large body of evaporitic Upper Triassic sequences. The other observation is that on surface, we have always marls and gypsum, so we do not have outcrops of salt or anhydrite. But the well data document that below the surface, it is very rich in these evaporitic minerals. So in these two composite sections using surface data and also surface information and wells, you can see that we are interpreting that most of the structure, the frontal structure of the Betics is formed by a very thick alloctonous nappe or canopy of Triassic evaporites. And you can see that we are interpreting imbricates of the Triassic evaporites overthrusting the foreland basin. But also you can also see that in the two sections using well data, we have a very important difference between the suprasalt sequences and the subsalt. So we can see that we have condensed sections on top and relatively thick thrusting sequences also detached in the Triassic evaporites below the alloctonous salt canopy. And also look at the scale. According to well data, well information, this is in cases near 3 kilometers in thickness of Triassic evaporites at the front of the external Betics. So one of the observations supporting this interpretation is that we have condensed sections on top of the alloctonous Triassic canopy, and compared to the subsalt sequence, we have here upper Jurassic Cretaceous strata with more than 1 kilometer below the salt, but above the canopy we have a condensed section with thin sequences of Jurassic, upper Jurassic, Cretaceous, and also Oligocene strata. So we do not have Miocene sequences below the salt. We have Miocene and Oligocene condensed sections above the alloctonous Triassic canopy. So this is one of the observations, in addition to the surface interpretation and the seismic interpretation, that we have an important salt structure that is incorporated in the fold and thrust belt. So other intriguing and important structure in the area is that on top of the alloctonous or the salt canopy, salt because in the subsurface is with salt, we have mini basins, tight and folded mini basins with Paleogene and Cretaceous strata, but also with Miocene strata. You can see here that we are interpreting the occurrence of overlapping geometries and also some mega flaps. And this mini basin is on top of the Triassic evaporites. An overview here in the field, you can see that the Triassic is overturned and is over a sequence in the mini basin from lower Cretaceous, upper Cretaceous, Oligocene, and lower Miocene. All the section is overturned in this limb of the mini basin. So it's really impossible to explain these geometries and sequences without using salt tectonic concepts. So to really go to the main point here in the Western Betics, we have suggested the occurrence of a previous salt canopy in the continental margin of the Betics, and this salt canopy was inverted due to thrusting of the internal Betics, producing shortening and inflation and overthrusting of the salt canopy toward the foreland basin. And in the Betics, we have identified the occurrence of mini basins on top of the alloctonous salt, some rafts or carapace that I didn't show in this presentation, and also a very important difference between the suprasalt and the subsalt sequences. So in other words, between the secondary mini basin and the primary basin. So this type of observations are probably important to take into consideration for the interpretation of other fold and thrust belts. So the other case is in Albania and Greece. So in this case, again, the upper Triassic evaporites are involved in this fold and thrust belt. We have three major thrust nappes detached along the Triassic evaporites, and all the Ionian from Albania to Greece, all the Ionian zone is the external part of the orogen is overthrusting the Apulian thick sequence of the carbonates that is like a buttress. The internal structure of the Hellenides is also showing how important are the Triassic evaporites, the upper Triassic evaporites, and also again, like in the Betics, the well data is documenting that in the subsurface we have halite and other evaporated minerals, because in the surface we only see brecciated rocks and gypsum. But look at the structural style in the orogen from Albania in the north, section 1, to Greece in the south. And you can see that we have different thrust sheets imbricating the Triassic evaporites. And in cases, we have areas with very thick accumulation of Triassic evaporites. So if we incorporate observations from seismic, for example, in Albania, like the Dumbre structure, look at it. We have near 6 kilometers of thickness of Triassic evaporites overthrusting lower Miocene strata. And on top of these bodies of Triassic structures, they are not covered by Miocene or even Pliocene strata. How to explain that? So we think that this region is also another example in where we have previous salt structures. For example, we can have salt pillows that they disappear laterally and they are at the base of thrust. In other cases, we have salt walls, and the salt walls are controlling the deformation and the structural style. They are also at the base of thrusting, but they are also conditioning or controlling the occurrence of major strike slip faults. This is an overview of some of the salt structures. And to go directly to the main points, for example, this is between Albania and Greece. This is the Butrinti area, and this is the major outcrop of Triassic. And according to well data, the Butrinti well, we have more than 3 kilometers of Triassic evaporites without any cover. And from one side to the other, you can see that the sequences are dipping against the body, against the accumulation. So also using seismic interpretation, we think that this is a salt wall, a salt plug, and the sequences are highly deformed and thicker in one flank and in the other. In cases they are dipping against the salt wall, and we do not have a roof on top of the salt wall. So I think that probably to open the eyes to these ideas that are not new, in the sense that previous diapirs are important to explain the geometries in a fold and thrust belt, let's use some experimental models by Tim Dooley. So in this case, the area is, let's see if the animation is running, or in this area, in this model, we have previous diapir, and the area diapirs, and the area is being deformed from the right to the left. The left is fixed. And look at the evolution of the salt diapirs. They change to be extrusive structures, and also look at the progression of thrusting being younger on the right, and you will see how the thrusting geometries are controlled by the position of the salt plugs, and you will identify that there is a young directions of thrusting toward the left. And also look at how we have salient and reentrance on the thrust due to the occurrence of the salt diapirs, or how some of the salt diapirs are producing extrusive flows and allochthonous structures on top. And we can also interpret it that most of the diapirs are deformed and translated toward the left. So the evolution in the salt structures is that at the beginning the two roofs are going closer, and they are producing a subvertical well. And the later evolution is that the vertical well is thrusted, and the upper part of the well of the diapir could produce also alloctonous structures. But this is not only the case, because in Greece we are also seeing walls, so it means elongated structures. They are not punctual. Let's use some modeling from Tim Dooley to inspect how different sal walls oriented differently according to the shortening. This is an east-west, so it's parallel to shortening. We have some walls that are oblique and some of them that are frontal. Let's see how the evolution of the model shows us a different structural style. So again, thrusting start in the hinterland and will be progressing younger toward the foreland. And look at how some of the sal walls are deforming with sigmoidal structures, with collapsed gravens on top, with extrusive features. And you will also see that the location of the sal walls are controlling the geometries of the fold and thrust belt. So to summarize, the main ideas is that sal walls that are parallel to shortening, they could be always open, like this structure in section A. They can also produce alloctonous structures on top. And the oblique structures like number 2 and number 3, they are welded, and the subvertical welds could be also overthrusted and producing these complex structures of vertical welds and thrust welds. So it is very important to consider the orientation and the dimensions of the walls with respect to the shortening direction. And to finish, this is the last, I'd like to propose some key observations to really reconstruct or evaluate if we have previous diapirs in an orogenic belt. First is that we can also have overlapping geometries near low relief structures like sal pillows. In other cases, we have also double virgin thrusting and pinch-off diapirs and thrust wells that are really very difficult to explain only with thrusting geometries. We have also number 3 locations in where we can have a very thick sequence on top of the Triassic, on top of the evaporites, and they decrease in thickness. And even we have omission and condensed sections on top of previous structures. So these are important observations to document the occurrence of previous diapirs. And finally, it's important to consider and to don't forget that the diapirs are the first who are absorbing shortening, and they are also controlling the final geometry of the thrust. So they are to really interpret the evolution of a fold and thrust belt, we need to interpret or to reconstruct the occurrence of previous diapirs. Well, I think that is probably too short, but I try to provide the main ideas to reconstruct these structures in a highly deformed fold and thrust belt.